Welcome back to the video course on fluid mechanics. In the last lecture, we were discussing about the various aspects of pipe flow system design. So, we have seen typically three varieties of problems. First problem is type 1 problems, where already the fluid properties like the density, the fluid viscosity, and then the velocity or discharge, and then the pipe properties like the diameter and the roughness height, these values are given. We have to find out the head loss. So, this we have seen that we can directly solve this problem by using the Darcy-Weisbach equation and related equations. That is type 1 problems, and then we have seen the type 2 problems. So, in the type 2 problems, the fluid properties like fluid density, dynamic coefficient viscosity, mu are given, and also the head loss is given due to the from one section to another, and also the pipe diameter and the roughness height is given. So, we have to find out the discharge or velocity passing through the pipe flow system. So, that is type 2 problem. So, this here we have seen by using various equations, we have to go through an iterative procedure to find out Q or V. Since the say without velocity we cannot calculate the Reynolds number. So, we will assume some friction value f, and then we will calculate the Reynolds number, and then we have seen that through an iterative procedure we will be solving these type 2 problems. The type 3 problems, it is given that the fluid properties like the fluid density, coefficient of dynamic viscosity is given, velocity is given, and the roughness height and head loss is given. We have to design the pipe, or we have to find out the diameter. So, here also we will be assuming certain values of f and the friction factor, and then we will be finding out the diameter of the pipe after through a iterative procedure as we discussed in the last lecture. So, now say we will go to some other systems of pipes like various say pipe in series, pipe in say parallel systems, and say with the branched piping system. So, before that, one more aspect we have to discuss here, that is the siphon. So, siphon is also one of the important system used in many of the say when to transfer fluid from one location to another, or different kinds of system. So, a typical siphon is shown in this slide here. So, you can see that here say what we are doing is, say if there are two reservoirs, one is at an upper elevation and other one is in the lower elevation. So, from upper elevation to transfer the fluid or water through a raised location. So, that is where we use the siphon. So, siphon is the closed conduit which lifts the liquid to an elevation greater than the free surface level and discharges it to a lower elevation. So, siphon is acting like this. So, here we have got a higher elevated reservoir and we have got a lower elevated reservoir B, and then, but we cannot directly, gravity flow is not possible, since if there is a raised portion here. So, through that raised portion we provide a pipeline, but you can see that here the uppermost the highest point in the pipeline is much above the reservoir A. So, but we are transferring the liquid or the water or fluid from A to B, but where B is at a lower position. So, it is a closed conduit which lifts the liquid at an elevation greater than the free surface level and discharges it to a lower elevation, as we have seen. So, here to operate the siphon system, it is necessary to exhaust air in the pipe by some means to start flow, and then the flow to continue also, the air collected at summit must be removed from time to time. So, to get a continuous flow we have to say to even to start the flow we have to remove the air inside the pipe, and then even to continue the flow we should say due to various say problems, air may collect on the top. So, we have to remove this air, and then you can see that there will be a low pressure at the raised position. So, due to the low pressure at point P, we can see that this continuous flow, there can be some interruption with respect to the flow, and there say this low pressure gives some limitations as far as the siphon is concerned. So, the siphon analysis we can do through the Bernoulli's equation and continuity equation, simple analysis we can do. Since here what we have to find out is we have to find out the either the pressure at the elevated location, or we have to find out the how much liquid has to be transferred, or we have to find out the head loss in the process. So, different kinds of problems which we discussed with respect to the pipe flow systems are applicable here also. So, we can use the Bernoulli's equation, simple Bernoulli's equations, and then we can also use the continuity equation together to get the various parameters with respect to the siphon. So, as we discussed here with respect to this siphon here. So, here if assuming the siphon is flowing full, we can apply the energy equation between sections A and B. So, section A and B means between the reservoir A and B here, between this location and this location. So, if you apply the energy equation, we can write H is equal to V square by 2 G plus K V square by 2 G plus FL V square by 2 G D, where V is the velocity of flow, F is the friction factor, L is the length of the siphon, D is the diameter of the siphon, G is the acceleration due to gravity, and K is the coefficient with respect to the minor losses. So, this gives the energy equation. So, now the solution procedure for H is straightforward, but in order to find the velocity V for the given H, we may have to go for trial and error solution with assumed value of the friction factor F. So, then if you want to find out the pressure at P as in figure. So, here at this rise location here, we want to find out the pressure will be much lower here, or sometimes it may be a negative pressure also. So, for here to find out the pressure at P as in figure, we can apply the energy equations between A and P, that will give P p by the energy equation between A and P gives P p by gamma is equal to minus Y p minus V square by 2 G into 1 plus K dash plus F L dash by D, where K dash is the minor loss coefficient and L dash is the length between A and P. So, here you can see that this Y p, this is from B to A, this is H here, and Y p is the vertical distance from A, this water level location, to the top point P. So, if you want to find out the pressure at P, so we can utilize this equation P p by gamma is equal to minus Y p minus V square by 2 G into 1 plus K dash plus F L dash by D, where K dash is the minor loss coefficient for the system and L dash is the length between A and P. So, like this siphon is concerned, we can say solve for the given system, whether we want to find out the H, that means the head loss, or whether we want to find out the velocity, or we want to find out any other parameter depending upon the different types of problems we discussed earlier. So, we can find out which type of problem we have to find out, and then we can either go for get a direct solution by using the Bernoulli's equation and the continuity equation, or we can go for a trial and error solution as we discussed in the earlier lecture. So, here, so as we have seen, this siphon is one of the important piping system. So, many places we use the siphon action or the siphon to transfer liquid from say one reservoir to another reservoir, whenever there is a elevated portion between the two reservoir. So, we can use the siphoning action, or we can use the principle behind the siphon. So, this is about the siphon. So, now next we will discuss the multiple piping systems. So far the problems which we discussed were related to a single pipe system when it is connected to a reservoir like that. So, now we will see we will discuss in detail about the multiple piping systems. So, most of the you can see that if we discuss about the water supply system, or when we deal with the various other piping system, either gas transfer or any other liquid transfer system, most of the times we will be dealing with multiple pipes, since say for long distance we cannot use a single pipe for transfer of liquid from one place to another. So, we will be using number of pipes, so that we have to deal with the multiple piping systems, and also many times many locations, many problems will be we have to deal with a divided flow. So, the flow will be coming from one location. So, you can see that if this is a reservoir here, and then if this is the pipe, then from say for example, just like in the case of water supply piping system. So, you can see that this is a depending upon the problem, we will be dividing, the flow will be dividing between one system to another, and then again there will be various branching like this. So, in all these systems you can see that we may have to deal with multiple piping systems with a flow divided, or the problem is a divided flow. You can see that the flow is starting from this location. So, it is flow is like this, but here you can see it is flowing like this, flowing like this. So, the flow is divided between the piping systems. So, the problems in these kinds of say whenever multiple pipe systems problems include the pipes in series, then looping pipes, branching pipes, and pipe networks. So, these typical problems in this multiple pipe system include the first case is the pipes in series. So, pipe in series is say when we are connecting say for example, a reservoir with respect to another reservoir. So, we may depending upon the case we may use different kinds of pipes, maybe large diameter or small diameter like this. So, it is pipe in series. So, here you can see that this is a typical case whenever the flow is, this is pipe in series. So, here the different pipes are connected serially. So, that is why we say that pipe flow is in series. So, pipe connection in series, and then we can sometimes we will be having depending upon the problem we may have pipes in parallel system. Say for example, we can have a piping system like this with respect to various systems. Say we can have different kinds of pipes in series, or this is called a pipe in parallel. So, this is another. So, first one is pipe in series, pipe in parallel system, and then as we have seen earlier, here you can see branched piping system. So, you can see that from one pipe to another it is branching. So, branched piping system, and then we can also have pipe networks. So, depending upon the problem, say for example, most of the water supply systems which we provide to cities, we will be having a network of piping systems going like this. So, it will be say depending upon the problem it may come and join with the same system. So, this is starting from if this is a piping system. So, where you can see that it will be coming back to the system. So, this is called a networking of piping between. So, you can see that if this is the reservoir, and here if you have got another system reservoir or another location, but you can see that there will be a loop here, one loop, another loop. So, this is pipe network system. So, depending upon the problem we will be having problem say with the multiple piping system, we may have series pipes, looping pipes, branching pipes, or pipe networks. So, we will be discussing each of these cases separately in detail, and most of this multiple piping system compared to the major losses, that means the friction losses which we calculate maybe using by Darcy-Weisbach equation, compared to this major losses, minor loss will be very small. So, depending upon the problem, say for some problems we may neglect the minor losses, but that also can be included in the calculation for better prediction. And also when we deal with the pipe flow system, the analogy between the pipe systems and electrical circuits also this is helpful in some of the calculations. So, we can have an analogy between the pipe flow system and the electrical circuit. So, the pipe flow analogy with respect to the electrical circuit. In the electrical circuit, we can see that it is a balance between the voltage E, current I and resistance R given by the Ohm's law, E is equal to I R. So, you can see that here this is for the electrical network or electrical circuit. So, similar way for fluid circuit, just like in the network, pipe network or the pipe flow system, we can see that there is a balance between the pressure drop, flow rate or velocity and flow resistance in terms of the friction factor, as we have seen the Darcy-Weisbach equation. So, we can have one-to-one correspondence with respect to the electrical circuit with say for example, if you just consider the Ohm's law, there with respect to that we can in a very similar way with an analogy between the say in the fluid circuit, we can compare with the pressure drop and pressure drop with respect to the voltage or the flow or velocity with respect to current, and then we can the resistance in an electrical circuit we can compare with respect to the flow resistance in terms of the friction factor, and then say we can compare with the Darcy-Weisbach equation which we have seen earlier with respect to the electrical corresponding electrical circuit system. Like that we can have an analogy, and then we can try to use this analogy for the solution of the pipe flow system. So, now we will discuss in detail the multiple pipe flow systems starting from pipe in series. We will discuss the pipe system in parallel, then branched pipe system, and also we will finally discuss the pipe network system. So, first one which we want to discuss here is the pipe systems in series. So, as we have seen earlier, so a pipe systems in series, it comprises of pipes connected one after another. So, you can see that as we have seen we have discussed earlier. So, if you want to connect between two reservoirs, say from A to B like this. So, instead of using a single pipe, since most of the time it will be difficult to use a single pipe if the distance between A and B is say large. So, we may use a number of pipes of maybe of different diameters. So, here you can see that one diameter is smaller diameter than larger diameter, like that a number of pipes are used here and connected serially. So, a specified number of say with respect to these connections, there will be say with respect to each pipe which are connected, there will be major losses, and also we can see that there will be minor loss components associated with each of the pipe elements. So, now we will discuss in detail how what kind of problems will be there with respect to the pipe systems in parallel, and then how to solve these kinds of problem when we deal with the pipe systems in parallel. So, we have seen that we have to consider the minor loss and also the major loss. So, as far as minor loss is concerned, we have seen earlier the minor loss can be written as HL is equal to K V square by 2 G, where K is the loss coefficient. So, this we can write in terms of discharge as K into Q square by 2 G A square, where A is the cross section area of the pipe. Now, let the frictional loss be, we can represent the frictional loss HL is equal to R Q square. So, with respect to this equation, we can write HL is equal to R Q square, where R is the resistance coefficient. So, where with respect to this equation, R is written as R is equal to FL by 2 GD A square, where F is the friction factor, L is the length of the pipe, G is the acceleration due to gravity, D is the diameter of the pipe, and A is the area of cross section of the pipe. So, we represent the head loss HL in terms of R Q square. So, now if we apply say with respect to this figure between A and B, if we apply the energy equation, we can write P by gamma plus Z at A minus P by gamma plus Z at B is equal to R1 plus sigma K 2 G A1 square into Q1 square plus R2 plus sigma K 2 G A2 square into Q2 square plus etc. So, for nth pipe we can write plus R n plus sigma k 2g a n square into q n square. So, that is equal to sigma I is equal to 1 to n R I plus sigma k divided by 2g a I square into q I square. So, where this R I is the resistance coefficient for the ith pipe as we calculated here, and then sigma k is the loss coefficient. So, here now this is the equation. So, when we write the energy equation between these two reservoirs, between two location A and B, we get this equation. So, here Z P by gamma is the pressure head and Z is the datum head if we consider this line as datum. So, what is the distance to the considered point? So, Z is the datum head. So, between this P by gamma plus Z at A and the P by gamma plus Z B. So, that difference is given by with respect to the summation sigma I is equal to 1 to n R I plus sigma k by 2 g A I square into q I square. So, where q I is the discharge through the ith pipe and A I is the area cross section of the ith pipe, and sigma k is the corresponding the loss coefficient, and then R I is the resistance coefficient for the ith pipe. So, this is the general equation for the head loss between, say, the energy equation when we apply the energy equation between A and B. This is the equation as in given in equation number 1. So, now for the series system from continuity and discharge through every element, we can see that when we apply the continuity equation, we can see that through every element the pipe flow element the discharge is same. So, we can write q 1 is equal to q 2 is equal to. So, n number of pipes are there. So, q 1 is equal to q 2 is equal to q 3, like that we can write. So, here as in equation number 2, q 1 is equal to q 2 is equal to q A is equal to q n. So, that is equal to q. So, you can see that any pipe the same discharge should be passing from A to B. So, that is coming from the continuity equation. So, now equation 1 with respect to this equation 1 here we can write P by gamma plus Z at A minus P by gamma plus Z at B is equal to sigma I is equal to 1 to n R I plus sigma k by 2 g I square into q square. Since discharge is same, instead of q I we can write q. So, it is q square as in equation number 3. So, in a series system the discharge remain constant. So, the losses, sum of minor losses and friction losses are accumulative, as you can see that here we are summing up with respect to pi 1 to n, we are adding up. So, including minor losses and the major friction losses we are adding. So, that we get the equation like this in as in 3. So, now say as we discussed earlier, for various pipe flow system we can have different types of problem. So, here also depending upon the problem we can have type 1, type 2, type 3 etc. different, say depending upon what parameters are available. If you want to calculate the other parameter, we can have type 1, type 2, type 3 etc. different problems. So, let us say see the series piping problem with respect to category 1 problem. So, the category 1 problem we have already seen, we have to find out the head loss between two locations. So, let us here two tanks are there and then 3 pipes are connected in series. So, for pipe 1, pipe 2, pipe 3, the diameter d 1, d 2 and d 3. So, here the known values are discharge, the diameters and the roughness height and also the kinematic viscosity nu. So, we want to compute the head loss HL. So, here we can calculate the friction and minor losses as we discussed in the last few slides, and we can directly get the HL, the head loss, by using this equation as in equation number 3. So, we can compute HL using formula 3 as given here, since this is a straightforward problem to find out the head loss HL. So, this is category 1 problem, and then for category 2 problem. So, here the known values are the diameter, the roughness height E and kinematic viscosity and also the head loss. So, here this is the kinematic viscosity and head loss if we want to find out the discharge Q. So, here you can see that since from one pipe to another, say here the discharge is not known, discharge is unknown. So, we cannot go for a straightforward solution, we have to go for a trial and error solution for this category 2 problem. So, here the diameter, reference height, kinematic viscosity and HL, the head losses are given. So, we have to find out Q. So, here the solution is not straightforward, we have to go for the trial and error solution. So, like this category 2 problem, and then say different other kinds of problems are also we can attempt with respect to the pipe in series problem which we discussed. So, here the say since the discharge is same, so Q1 is equal to Q2 is equal to Q3 and depending upon number of pipes, and then we have to use the energy equation which we have seen here. So, that is the general approach, and only difference is that whether the depending upon the problem the solution may be straightforward or we have to go for a trial and error solution, as we discussed in the earlier lecture with respect to the various available values, and with respect to say if you want to find out the discharge or if you want to find out the design the pipe or diameter of the pipe, if you want to find out, we have to go for a trial and error solution. So, here now we will consider an example problem. So, the example problem is say there are two tanks are there. So, one tank is here A and the second tank is here tank or reservoir B. So, here this reservoir B is under pressure and here this is open to atmosphere. So, we connect the reservoirs from A to B through a piping system. So, we have got a pipe here with and then there is a pumping system. So, through this only we pump, and here there is a valve to control the flow, and then it is connected like this, and then finally it joins the reservoir at B. So, we had to find the required power to pump say 200 liters per second of liquids with a specific gravity 0.85 and kinematic viscosity 10 to the power minus 5 meter square per second. So, this is the problem, and the pump is operating at an efficiency eta is equal to 0.75 and the pressure at B should be 210 per meter square. So, here the reservoir or the tank at B is under pressure or 210 per meter square, but at A it is open to atmosphere. So, various the discharge to be passed is 200 liters per second, and the kinematic viscosity is given 10 to the power minus 5 meter square per second. So, now the various other data given are here. Now, from figure at line 1, here this length, line 1 length is L is equal to 10 meter and diameter is 0.2 meter, and the reference height is E is equal to 0.05 millimeter, and this K1 here this K1, the entry loss K1 is 0.5 and the valve loss here we have got a valve. So, with respect to this loss Kb is equal to 2. And similarly, this say so line 1 is up to here, and for line 2 this is line 2. So, for line 2 the length is given as 500 meter and the diameter is given as 0.25 meter, and the reference height with respect to the pipe is given as 0.05 millimeter, and here this Ke say due to the bend here. So, here Ke is given as 0.25 and K2, that means the exit loss here with respect to this K2 here is given as 1. So, these are the parameters. So, this is here the question here is to we want to find out the required power to pump. So, actually this is a type 1 problem where most of the parameters are directly given. So, to solve this problem we will just use the energy equation between reservoir A and B. So, we will apply the energy equation. So, energy equation is P by gamma plus Z at A plus the pumping say HP corresponding to the head related to the pump HP, that is equal to P by gamma plus Z with respect to reservoir B plus R1 for the pipe 1, the resistance coefficient for pipe 1 plus K1 plus KV, K1 is the entry loss, KV is the valve loss divided by 2G A1 square plus R2 the resistance coefficient for pipe 2 plus 2 KE the bend losses plus K2 the exit loss divided by 2G A2 square the area cross section of pipe 2 into Q square. So, this is the energy relationship between A to B as we discussed. So, now here most of the parameters we want to find out, say other than HP, most of the parameters are known. HP is the head across the pump which we have to find out. So, now we have to find out the Reynolds number and say the relative roughness. So, for line 1, the Reynolds number is for the pipe, it is Vd by nu, that is the Reynolds number equation for pipe. So, we can transfer, we can write in terms of the discharge as Reynolds number is equal to 4q divided by pi d 1 nu. So, here 4 is 4 into q is 0.2 divided by pi into d 1 is 0.2 into 10 to the power minus 5 as given by kinematic viscosity nu here. So, this is equal to 1.27 into 10 to the power 5 and then E by D ratio will be 0.05 divided by 200, that will be equal to 0.00025. So, similarly, for line 2 Re2 is equal to 4q by pi d2 nu, that is equal to 4 into 0.2 divided by pi into 0.25 into 10 to the power minus 5, that will be obtained as 1.018 into 10 to the power 5. So, similar way E by D ratio will be 0.05 by 250, it is equal to 0.0002. So, now to solve this problem, different equations, different formulas are available in the literature. So, here we will use the Samy and Jain formula which we discussed earlier. We can solve can use other equations also to solve this problem, but here we adopt the Samy and Jain formula to solve. So, here with respect to Samy and Jain formula, we have seen the resistance coefficient we can write as R is equal to, we can derive as we discussed earlier about the Samy and Jain formula. We have seen various equations with respect to friction factor, HL, head loss and Q. We have seen the equation. So, from that we can derive the Samy and Jain formula as R is equal to 1.07 into L by G into d to the power 5 into natural log 0.27 into E by D plus 5.74 into 1 by Re to the power 0.9 all to the power minus 2, where R is the Reynolds number and E by D is the relative roughness. So, this relationship is given by Samy and Jain. So, now if you use the Samy and Jain equation here, we can calculate the resistance coefficient for each pipeline. So, if you consider pipeline number 1, so just substituting all the values, R1 will be obtained as 1.07 into length is 10 by 9.81 into 0.2 to the power 5 into natural log 0.27 into 0.00025 plus 5.74 into 1 by the Reynolds number 1.27 into 10 to the power 5 all to the power 0.9 and again all to the power minus 2. So, we will get as R1 as 47.71. Similarly, we can get R2, the value of R2 is will be 797.86, and then in this equation we can calculate with respect to the minor loss coefficient, we can calculate K1 plus Kv by 2G A1 square is equal to 0.5 plus Kv is given as 2. So, here Kv is already given as 2. So, if you use Kv 0.5 plus 2 divided by 2 into 9.81 into pi by 4 into 0.2 all square. So, that is equal to 129.1. So, similar way for pipeline 2 Ke plus K2 by 2 Ag 2 square will be obtained as 31.7. So, we can substitute now in the energy equation which we are written here, this is the energy equation. So, if you substitute back in the energy equation, we get, so here this here initially for the problem this is under atmospheric pressure. So, P by gamma will be 0. So, P by gamma corresponding the elevation is given as 20. So, P by gamma plus 20 plus Hp is equal to 200 into 1000 by 0.985 0.85 into 9810 when we transform with respect to the pressure at reservoir B. So, plus 40 is the elevation here 40. So, plus 47.71 which is R1 plus 129.1 plus 797.86 plus 31.7 into 0.2 square. So, from this we will get the value of Hp. So, here the head across the pump Hp is equal to 84.23 and then we can find out the required input power Wp is equal to gamma q hp by eta. So, gamma is 9810 into 0.85 the specific gravity into q is 0.2, hp is 84.23 divided by 0.75. So, thus we get Wp, the input power required is 18.73 into 10 to the power 4 watts or 187.3 kilowatts. So, like this, so we have seen now one of the example of the pipes in series. So, like this different kinds of problem we can solve either using the depending upon what kind of parameters are already available and what we are going to determine. So, here we with respect to head loss we found how much is the power requirement. So, this is a straightforward problem which we have solved here, but other way if you want to find out for the given piping system, if you want to find out the discharge or if you want to find out other parameters, we may be say like in category 2 or type 2 and type 3 problems, we will be using iterative techniques as we discussed in the earlier lecture. So, that is about the pipe system in series. So, different kinds of problems can be there depending upon what kind of data is available and what we are trying to solve. So, now the next case is piping system in parallel. So, as we have seen earlier, there can be different cases for piping system in parallel. So, first one is pipe system in series we have seen. So, now we will consider a piping system in parallel. So, here there are two reservoirs and then we can see that the reservoir is connected through two pipes which are in parallel. So, for this arrangement, so here we have shown in this slide two pipes are shown, there can be n number of pipes elements joined between A and B with the sigma k minor loss components associated with each pipe element I. So, there can be here only two pipes are shown like that 1, 2, 3 n pipes can be there with the sigma k minor loss and then say we can connect between A and B. So, now here also we can use the continuity equation and then we can use the energy equation. Same from the continuity equation we can see that total discharge Q is equal to sigma I is equal to 1 to n Q I. So, here when we consider 1, 2, 3 pipes. So, with respect to this total discharge should be equal to whatever the discharge in pipe 1 plus pipe 2 plus pipe 3 like that. So, Q is equal to sigma I is equal to 1 to n Q I, and the algebraic sum of the energy gradient line around any defined loop must be 0. So, as we have seen we can apply the energy equation. So, the algebraic sum of the energy gradient line around any defined loop must be 0. So, that gives the second equation, and most of the time we assume this kinds of problem the velocity head v square by 2 g is less than the with respect to c into p by gamma plus z, where the head loss with respect to the energy with respect to the pressure and the datum head and pressure head. So, it will be this velocity head will be much lower, much less compared to this parameter. So, where c is a coefficient depending upon the problem. So, for any pipe element I, by using the energy equation, so two equations are available, one is the continuity equation and the second equation is the energy equation. So, we can write the energy equation between A and B. So, that will give P by gamma plus Z at A minus P by gamma plus Z at B, that is equal to R I plus sigma k by 2 g A I square into Q I square. So, where Q I is the discharge in pipe number I and A is the cross section of pipe number I, and R I is the resistance coefficient with respect to pipe number I, as we have discussed in the previous slides for the pipe in series. So, here I ranges from 1 to number of pipes. So, this the basic equations which we here also which we use for pipes in parallel, one is the continuity equation and the second one is the energy equation depending upon the problem. So, here the unknown in equation is discharge and equation 2 is the difference in piezometric head between A and B. So, equation number 1 is coming from the continuity equation and equation 2 is the difference in piezometric head between A and B. So, the discharge into the system is known, the total discharge is known. So, it is possible to convert the minor loss terms using an equivalent length E. So, we have already seen how to use the equivalent length earlier. So, we can use the equation for equivalent length as we discussed earlier. So, the equation corresponding to equivalent length can be written as LEI is equal to DI by Fi into sigma k, where d is the diameter of the corresponding pipe and Fi is the friction factor and sigma k is the loss coefficient. So, L is equal to di by Fi into sigma k as given in this equation number 3, and then equation 2 can be simplified. So, here this equation we can simplify if you use this here as P by gamma plus Z for A minus P by gamma plus Z for B is equal to Ri bar Qi square, where Ri is the modified pipe resistance given us. So, here we can convert this with respect to the modified pipe resistance as 8 Fi into Li plus Lei divided by G pi square di to the power 5. So, here Le is the equivalent length for the minor loss and Li is the pipe length which we consider, and then this di is the diameter and Fi is corresponding friction factor. So, the modified pipe resistance we can obtain as in equation number 5. So, solution for the above this we can use the method of successive substitution. So, here also a direct solution is not possible, since we only know the total discharge. So, we do not know the discharge with respect to the individual pipes. So, we have to go for a successive substitution. So, here we use the method of successive substitution. So, here the solution by method of successive substitution is described in detail. So, here if the piezometric difference between A and B, that is, let us write W is equal to P by gamma plus Z at A minus P by gamma plus Z at B. So, that we can write with respect to this equation here, that means equation number 4, we can write Qi is equal to square root of W by Ri bar, where Ri bar is the modified pipe resistance as in equation number 6. So, we can use now equation number 1 and 6. Equation number 1 here is the continuity equation. From the continuity equation, Q is equal to sigma I is equal to 1 to n Qi. So, now equation 1 and this equation 6 we can use to eliminate the unknown. So, that we can get Q is equal to sigma I is equal to 1 to n square root of W by Ri bar, and that will be equal to root W is taken out. It will be root W into sigma is equal to 1 to n square root of 1 by Ri bar. So, since here now the total discharge is known, so we can sum it up. So, by using equation number 1 and 6 we get equation number 7, and now we can solve for W as W is equal to Q by sigma is equal to 1 to n 1 by root Ri bar whole square as shown in equation number 8. So, here this equation 6, 7, 8 and 1 we will be using for the solution. So, we use here an iterative procedure to solve for this W, which is the piezometric difference between A and B, to solve W and Qi, the discharge through each pipe. So, the iterative procedure is the steps are listed here. So, first one is we assume the flows in each line to be in completely rough zone and compute the initial estimate of friction factor in each line using the equation. So, here also as I mentioned there can be different methodologies and different approaches are possible. So, for the demonstration purpose here I use the Swami and Jain formula. So, here since the discharge is not known, so we initially use a part of the Swami and Jain formula. So, original Swami and Jain formula for friction factor is given like this, but here we cannot the first iteration we do not know the velocity through the pipe or the discharge through individual pipe. So, Re is not known. So, this part is deleted. So, for the initial approximation we write F is equal to 1.325 into natural log 0.27 E by D all to the power minus 2 as in this equation. And then second step is compute Ri bar, that means the equivalent resistance as given here for each pipe, and evaluate W by using this equation. We can evaluate equation Ri bar and evaluate W with respect to equation 8. Then compute Qi in each pipe by using equation number 6. So, here we use an iterative procedure. We start with we assume flows in each line to be completely rough zone, and then we use Swami and Jain formula to get F, and then we compute Ri bar and then evaluate W, and finally, we compute Qi in each pipe by using equation number 6. Then in step number 4 we update estimates of friction factor in each line using the current value of Qi in equation, in full equation of the Samy and Jain formula for friction factor as given here. F is equal to 1.325 natural log 0.27 into E by D plus 5.74 into 1 by RE to the power 0.9 all to the power minus 2. So, here then we will repeat steps 2 to 4 until the unknown W and Qi do not vary according to a desired tolerance. So, we can fix a tolerance whether 0.0001 or 0.001, like that we can put a tolerance, and then we will do the iteration and we will repeat the steps 2 and 4. So, here as a demonstration, here a problem is solved. So, here the problem is there are 3 pipes in parallel and the total discharge is known. So, find the distribution of flow and drop in hydraulic grade line P by gamma plus Z for the 3 parallel pipes arranged as shown in figure. Use variable friction factors, and the kinematic viscosity nu is given as 10 to the power minus 6 meters per second, and the total water discharge total Q is known as 0.04 meters cube per second. So, here we want to find out the distribution of flow in pipe 1, 2, 3, and various parameters given are: for pipe 1 the length is 200 meter, diameter is 0.05 meter, E is 0. The roughness height is 0.0001 and sigma k is 10, and for pipe 2 length is 300, diameter is 0.075 meter and E is 0.0002 meter and sigma k is 3, and for pipe 3 length is 400 and D is 0.085 and E is 0.0001 and sigma k is 2. So, as we have seen in the here the iterative procedure steps 1 to 5. So, here we use, so initially we estimate the friction factor from the some part of the Samy and Jain formula. Since Reynolds number is not known, we will use this equation. So, for pipe 1, 2, 3 we calculate E by D like this and the friction factor, and then also we calculate the equivalent length LE, and then we find out the resistance equivalent resistance coefficient as shown here. Here this equivalent modified pipe resistance is calculated here. So, these values are given here for pipe 1, pipe 2 and pipe 3. So, E by D 0.002 for pipe 1, pipe 2 0.0027, pipe 3 0.0012, and then we calculate F 0.023, 0.025, 0.021, and the equivalent length is 21.7, 9, 8.1, and we find R bar as 13.48 into 10 to the power 5, 2.69 into 10 to the power 5 and 15.96 into 10 to the power 4. So, then using equation 8 as we discussed earlier, we can now find out W. So, here Q is known 0.04 and then this values R bar is already calculated. So, R bar to the power minus half. So, and then sum up and all square. So, that gives, so here we have seen this W is this equation number 8. So, we use this equation number 8, we get here W as 57.15 meter, and then we use this equation number 6 here. We have this equation number 6. We will calculate now the discharge through individual pipes Qy. So, Q1 we calculate by using this 57.15 W, we get 0.0065 meter cube per second, and Q3 as 0.0189 cubic meter per second, and Q2 as 0.01458 cubic meter per second. So, you can see that if we add it up, we will get as 0.0398 meter cube per second. So, we have to, the total discharge given is 0.04 meter cube per second. So, we have to again go for one more iteration. So, here now the second iteration, now each the discharge through each pipe is even though it is not exact, it is known. So, using that we can use the full Samy and Jain formula as given here. So, correspondingly for pipe 1, 2, 3 we can find out the Reynolds number Vd by nu or 4q by pi d nu, and these are given here, and correspondingly we can calculate the friction factor F1, F2, F3 with respect to this Reynolds number by using this equation Samy and Jain formula, and then we find out R bar as in equation number 5, and then again we evaluate W as in equation number 8, and here we get a W of say 130.99, and again we substitute in equation 6 to find out Qi. So, finally, we get Q1 is equal to 0.0113 meter cube per second, Q2 is equal to 0.0139 meter cube per second, and Q3 is 0.01478 meter cube per second. So, if we add all the discharges, we will see that it will be almost equal to 0.04 meter cube per second. So, like this we can continue until we reach the solution, we can continue the iteration and we can find out the discharge through each pipe, and then we can go for other solution. So, this is a typical example solved. So, like this, as far as parallel system is concerned, we can solve for unknown, we can find out the unknowns by using the various relationship, various equation which we have discussed here. So, in the next lecture we will be discussing the branch pipe systems and the pipe network system with respect to the various equations we will be discussing.